Welcome to this comprehensive journey through Calculus 1. Over the next 2 hours, we're going to explore one of the most powerful mathematical tools ever created. But before we dive into formulas and techniques, let's start with a simple question. What is calculus, and why should you care? Calculus is the mathematics of change. While algebra deals with fixed quantities, calculus allows us to understand things that are constantly moving, growing, or transforming. Think about a car accelerating down a highway. Algebra can tell you the distance traveled if you know the speed and time. But what if the speed is changing every second? That's where calculus comes in. Calculus lets us analyze motion, growth, decay, and optimization in ways that would be impossible with algebra alone. The story of calculus begins in the 17th century, with two brilliant minds working independently: Isaac Newton in England and Gottfried Leibniz in Germany. Both were trying to solve problems in physics and mathematics that required understanding instantaneous rates of change. Newton wanted to describe planetary motion and the laws of physics. Leibniz was interested in the geometric properties of curves. They both arrived at similar conclusions, though with different notations. Today, we actually use Leibniz's notation more commonly because it's more intuitive for many applications. Calculus has two main branches. Differential calculus deals with rates of change and slopes of curves. It answers questions like how fast is this changing right now? Integral calculus deals with accumulation and areas under curves. It answers questions like how much has accumulated over this time period. These two branches are intimately connected through what we call the fundamental theorem of calculus, which we'll explore later in this video. The applications of calculus are everywhere. In physics, calculus describes motion, energy, and forces. In engineering, it's used to design bridges, optimize circuits, and model fluid flow. In economics, calculus helps us understand marginal costs and maximize profits. In biology, it models population growth and the spread of diseases. In medicine, calculus helps us understand how drugs are absorbed and metabolized in the body. Even in computer graphics, calculus is used to create smooth animations and realistic lighting. If you're studying any field of science, engineering, economics, or applied mathematics, you will use calculus. Now, let's begin our journey by understanding the foundation of all calculus: the concept of a limit. The limit is the most fundamental concept in calculus. Everything else we do, derivatives, integrals, everything, builds on limits. So what exactly is a limit? Let's start with an intuitive example. Imagine you're walking toward a wall. You start 10 feet away. Then you walk halfway to the wall, so now you're 5 feet away. Then you walk half of the remaining distance, so you're 2.5 feet away. Then you walk half of that distance and you're 1.25 feet away. You keep doing this, always walking exactly half of the remaining distance. Here's the question: will you ever reach the wall? Mathematically, no. There's always some tiny distance remaining. But here's the key insight. You can get as close to the wall as you want. If someone asks you to get within 1 inch of the wall, you can do it. Within 1 millimeter, you can do that too. Within 1 nanometer. Given enough steps, yes, this is the essence of a limit. You approach a value, getting arbitrarily close, even if you never quite reach it. In mathematical notation, we write this as the limit of f of x. As x approaches a equals L. This means as x gets closer and closer to the value equal, the function f of x gets closer and closer to the value L. Notice the language here. Approaches, not reaches. That's crucial. Let's consider a concrete mathematical example. Look at the function f of x equals x squared minus 1, all divided by x minus 1. Now, if we try to plug in x equals 1, we get 0 divided by 0, which is undefined. We can't evaluate the function at x equals 1. But we can ask, what happens as x approaches 1? Let's try some values. If x equals 1.1, we get 1.1 squared minus 1, divided by 1.1 minus 1, which equals 2.1. If x equals 1.01, we get approximately 2.01. If x equals 1.001, we get approximately 2.001. Do you see the pattern? As x gets closer to 1, the function value gets closer to 2. We can also approach from the other side. If x equals 0.9, the function value is 1.9. If x equals 0.99, we get 1.99. If x equals 0.999, we get 1.999. Again, approaching 2, so even though we can't evaluate the function exactly at x equals 1, we can say with confidence that the limit as x approaches 1 of this function is 2. This is a removable discontinuity, sometimes called a hole in the graph. The function is undefined at that point, but the limit still exists. Here's an important distinction. The limit as x approaches a does not depend on what happens at x equals a. It only depends on what happens near x equals a. The function doesn't even need to be defined at that point for the limit to exist. This is counterintuitive at first, but it's absolutely crucial to understanding calculus. Let's talk about one-sided limits. Sometimes we need to be more specific about how we're approaching a value. We can approach from the left, meaning from values smaller than a, or from the right, meaning from values larger than a. We call these the left-hand limit and the right-hand limit. Consider the absolute value function divided by x. For positive values of x, the absolute value of x is just x, so the function equals 1. For negative values of x, the absolute value of x is negative x, so the absolute function equals negative 1. At x equals 0, the function is undefined. Now, what's the limit as x approaches 0? Well, if we approach from the right, meaning from positive values, the function is always 1, so the right-hand limit is 1. If we approach from the left, meaning from negative values, the function is always negative 1, so the left-hand limit is negative 1. Since the left-hand limit and right-hand limit are different, we say the limit does not exist. For a limit to exist at a point, the left-hand limit and right-hand limit must be equal. This is a formal requirement, and it's important for understanding continuity. Now let's discuss some limit laws. These are rules that let us calculate limits algebraically without having to plug in values. If the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals m, then we have several useful properties. The limit of a sum is the sum of the limits. The limit as x approaches a of f of x plus g of x equals L plus m. The limit of a difference is the difference of the limits. The limit of a constant times a function is the constant times the limit of the function. The limit of a product is the product of the limits. And the limit of a quotient is the quotient of the limits, provided the denominator limit is not 0. These laws make our lives much easier. For example, to find the limit as x approaches 3 of 2x squared plus 5x minus 1, we can break this down. The limit of 2x squared as x approaches 3 is 2 times the limit of x squared, which is 2 times 9, which equals 18. The limit of 5x is 5 times 3, which equals 15. The limit of negative 1 is just negative 1. Adding these together, we get 18 plus 15 minus 1, which equals 32. For polynomial functions like this one, the limit as x approaches a is simply f of a. You just plug in the value. The same is true for most elementary functions like exponentials, logarithms, trig functions, and so on, as long as they're defined at that point. But what about more complicated situations? Let's talk about limits at infinity. What happens to a function as x gets larger and larger, approaching infinity? This is important for understanding the long-term behavior of functions. Consider f of x equals 1 over x. As x gets larger, 1 over x gets smaller. When x equals 10, f of x equals 0.1. When x equals 100, f of x equals 0.01. When x equals 1000, f of x equals 0.001. As x approaches infinity, f of x approaches 0. We write this as the limit as x approaches infinity of 1 over x equals 0. Now consider f of x equals x squared over x squared plus 1. As x gets very large, both the numerator and denominator grow, but they grow at the same rate because they're both dominated by the x squared term. If we divide both numerator and denominator by x squared, we get 1 divided by 1 plus 1 over x squared. As x approaches infinity, 1 over x squared approaches 0, so we're left with 1 divided by 1 plus 0, which equals 1. The limit as x approaches infinity of this function is 1. This technique of dividing by the highest power is extremely useful for rational functions. For the limit as x approaches infinity of a rational function, divide the numerator and denominator by the highest power of x in the denominator, then evaluate. Let's discuss infinite limits. Sometimes a function grows without bound as x approaches a certain value. Consider f of x equals 1 over x squared. As x approaches 0, the denominator gets smaller and smaller, so the function value gets larger and larger. We say the limit as x approaches 0 of 1 over x squared equals infinity. This doesn't mean the limit exists in the usual sense. It's a way of describing the specific manner in which the limit fails to exist. Similarly, for f of x equals 1 over x, as x approaches 0 from the right, the function approaches positive infinity. As x approaches 0 from the left, the function approaches negative infinity. We need to specify the direction when the behavior is different from each side. A vertical asymptote occurs when a function approaches infinity, or negative infinity as x approaches some value. The line x equals a is a vertical asymptote if the function grows without bound near x equals a. For example, x equals 0 is a vertical asymptote for fams of x equals 1 over x. A horizontal asymptote occurs when a function approaches some finite value, as x approaches infinity or negative infinity. The line y equals L is a horizontal asymptote if the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity equals L. For example, y equals 0 is a horizontal asymptote for f of x equals 1 over x. Now let's talk about continuity. Intuitively, a function is continuous if you can draw its graph without lifting your pencil from the paper. More formally, a function f is continuous at x equals a if 3 conditions are met. First, f of a must be defined. Second, the limit as x approaches a sine of f of x must exist. Third, the limit must equal f of a. All 3 conditions are necessary. If the function isn't defined at a point, it can't be continuous there. If the limit doesn't exist, it's not continuous. And even if both the function value and limit exist, they must be equal for continuity. Polynomial functions are continuous everywhere. Rational functions are continuous wherever they're defined, meaning wherever the denominator isn't 0. Exponential and logarithmic functions are continuous on their domains. Trigonometric functions are continuous on their domains. Compositions of continuous functions are continuous. There are three main types of discontinuities. A removable discontinuity, or hole, occurs when the limit exists, but either the function isn't defined there, or the function value doesn't equal the limit. We saw this earlier with x squared minus 1 over x minus 1 at x equals 1. A jump discontinuity occurs when the left-hand and right-hand limits exist, but are not equal. Think of a step function that jumps from one value to another. An infinite discontinuity occurs when the function approaches infinity or negative infinity at that point. This happens at vertical asymptotes. The intermediate value theorem is a powerful result about continuous functions. It states that if f is continuous on the closed interval from a to b, and n is any number between f of a and f of b, then there exists some c in the interval where f of c equals n. In other words, a continuous function takes on every value between its endpoint values. This might seem obvious, but it's actually quite profound. It guarantees the existence of solutions to equations. For example, if we want to solve x cubed minus x minus 2 equals 0, we can define f of x equals x cubed minus x minus 2. When x equals 1, f of x equals negative 2. When x equals 2, f of x equals 4. Since f is continuous and 0 is between negative 2 and 4, there must be some value between 1 and 2 where f equals 0. This guarantees a solution exists, even if we can't find it algebraically. The squeeze theorem, also called the sandwich theorem, is another important limit tool. If g of x is less than or equal to f of x is less than or equal to h of x for all x near a, and the limit as x approaches a of g of x equals the limit as x approaches a of h of x equals L, then the limit as x approaches b of f of x also equals L. The function f is squeezed between g and h, so it must approach the same limit. A classic application involves the limit as x approaches 0 of sine x over x. This is not obvious because both the numerator and denominator approach 0. But using geometry and the squeeze theorem, we can show this limit equals 1. This result is fundamental to finding the derivative of sin x. Let me emphasize something important about limits. When we write the limit as x approaches a of f of x equals L, we're making a very precise mathematical statement. For any positive epsilon, no matter how small, there exists a positive delta, such that if x is within delta of a but not equal to a, then f of x is within epsilon of L. This is the formal epsilon delta definition of a limit. You might not use this definition for calculations, but it's the rigorous foundation that makes calculus work. Understanding limits takes practice. You need to develop intuition for how functions behave near points of interest. You need to recognize when direct substitution works and when you need to use algebraic manipulation, limit laws, or special techniques. But once you master limits, you have the key to unlock all of calculus. This concludes our foundations and limits section. We've covered what calculus is, why it matters, the intuitive and formal understanding of limits, one-sided limits, limits at infinity, infinite limits, continuity, and important theorems about limits. These concepts form the bedrock upon which we'll build everything else. In the next section, we'll see how limits let us define the derivative, which is the cornerstone of differential calculus. Now that we understand limits, we can tackle the derivative, which is arguably the most important concept in differential calculus. The derivative measures how fast something is changing. It's the instantaneous rate of change, and it forms the basis for solving countless problems in science, engineering, and beyond. Let's start with a fundamental question. What is the slope of a curve? You probably remember from algebra that the slope of a straight line is rise over run, or the change in y divided by the change in x. But what about a curve? A curve doesn't have a single slope. It's constantly changing direction. At different points, it's steeper or flatter. So how do we define the slope at a single point on a curve? The answer involves limits. Imagine you have a curve and you want to find the slope at a particular point. Let's call it point P. We can't just use 2 points on the curve to calculate slope like we would for a line, because that would give us an average slope over an interval, not the exact slope at P. But here's the clever idea. We can take another point Q on the curve, calculate the slope of the line through P and Q, then let Q move closer and closer to P. As Q approaches P, the slope of that line approaches the slope of the curve at P. This line through P and Q is called a secant line. As Q moves toward P, the secant line rotates and approaches what we call the tangent line, the line that just touches the curve at P. The slope of the tangent line is the slope of the curve at that point, and this is exactly what the derivative gives us. Let's make this precise. Suppose we have a function f, and we want to find the derivative at x equals a. We consider another point nearby at x equals a plus h, where h is some small number. The slope of the secant line through these 2 points is f of a plus h minus f of a, all divided by h. This is just rise over run. Now we take the limit as h approaches 0. This limit, if it exists, is the derivative of f at x equals a. We can also think of the derivative more generally as a function itself. The derivative of f, written as f prime, is defined as the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. This definition works at every point where the limit exists. Let's compute a derivative from first principles using this definition. Consider f of x equals x squared. We want to find f prime of ax. Using the definition, f prime of x equals the limit as h approaches 0 of x plus h squared minus x squared, all divided by h. Let's expand x plus h squared. That's x squared plus 2xh plus h squared. So we have x squared plus 2xh plus h squared minus x squared all over h, the x. Squared terms cancel, leaving 2xh plus h squared all over h. We can factor out h from the numerator, giving us h times 2x plus h all over h. The h cancels, leaving 2x plus h. Now we take the limit as h approaches 0, which gives us 2x. So the derivative of x squared is 2x. This tells us something beautiful. At any point x on the curve, y equals x squared. The slope of the tangent line is 2x. When x equals 1, the slope is 2. When x equals 3, the slope is 6. When x equals negative 2, the slope is negative 4. The derivative function tells us the slope at every single point. Let's try another example. Consider f of x equals 1 over x. Using the definition, f prime of x equals the limit as h approaches 0 of 1 over x plus h minus 1 over x, all divided by h. To combine those fractions in the numerator, we need a common denominator. That gives us x minus x plus h, all over x times x plus h, divided by h. Simplifying the numerator, we get negative h over x times x plus h, divided by h. We can rewrite this as negative h over x times x plus h, times 1 over h, which is negative 1 over x times x plus h. Now, taking the limit as h approaches 0, we get negative 1 over x squared, so the derivative of 1 over x is negative 1 over x squared. Computing derivatives from the limit definition every time would be tedious. Fortunately, we have derivative rules that make this much easier. Let's go through the most important ones. The power rule is probably the most useful derivative rule. If f of x equals x to the power n, where n is any real number, then f prime of x equals n times x to the power n minus 1. You bring down the exponent as a coefficient and reduce the exponent by 1. So the derivative of x cubed is 3x squared. The derivative of x to the fifth is 5x to the fourth. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. The derivative of x to the negative 3 is negative 3x to the negative 4. The constant rule says that the derivative of a constant is 0. This makes sense because a constant doesn't change. There's no rate of change. So the derivative of 7 is 0. The derivative of pi is 0. The derivative of any number is 0. The constant multiple rule says that the derivative of a constant times a function is the constant times the derivative of the function. If f of x equals c times g of x, then f prime of x equals c times g prime of x. You can pull constants out in front of the derivative. So the derivative of 5x cubed is 5 times 3x squared, which equals 15x squared. The sum rule says that the derivative of a sum is the sum of the derivatives. If f of x equals g of x plus h of x, then f prime of x equals g prime of x plus h prime of x. The same applies to differences. You can take derivatives term by term. So to find the derivative of 3x squared plus 4, x minus 7, we take the derivative of each term separately. The derivative of 3x squared is 6x. The derivative of 4x is 4. The derivative of negative 7 is 0. Adding these up, we get 6x plus 4. These rules combine to let you differentiate any polynomial quickly. Just apply the power rule to each term, multiply by any coefficients, and add them up. Now let's talk about the product rule. This one is less intuitive. You might think the derivative of f times g would be f prime times g prime, but that's wrong. The correct product rule is, if h of x equals f of x times g of x, then h prime of x equals f prime of x times g of x plus f of x times g prime of x. The derivative of the first times the second plus the first times the derivative of the second. Let's use this to find the derivative of x squared times sin ax. Let f of x equal x squared and g of x equal sin ax. Then f prime of x equals 2x and g prime of x equals cosine x. Using the product rule, the derivative is 2x times sin x plus x squared times cosine x. Notice we needed to know that the derivative of sin x is cosine x. We'll come back to trigonometric derivatives in a moment. The quotient rule is for derivatives of fractions. If h of x equals f of x divided by g of x, then h prime of x equals f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. A helpful mnemonic is low d high minus high d low over the square of what's below. Low means the denominator, high means the numerator, and d means derivative. Let's differentiate x squared plus 1, all divided by x minus 3. Let f of x equal x squared plus 1, so f prime of x equals 2x. Let g of x equal x minus 3, so g prime of x equals 1. Using the quotient rule, the derivative is 2x times x minus 3, minus x squared plus 1 times 1, all over x minus 3 squared. Simplifying the numerator, we get 2x squared minus 6x minus x squared minus 1, which is x squared minus 6x minus 1. So the answer is x squared minus 6, x minus 1, all over x minus 3 squared. The chain rule is perhaps the most powerful and important derivative rule. It tells us how to differentiate composite functions. If h of x equals f of g of x, meaning you apply g first then f, then h prime of x equals f prime of g of x times g prime of x. In Leibniz notation, if y is a function of u and u is a function of x, then di dx equals di du times du dx. Let's see this in action. Consider h of x equals the quantity x squared plus 1 raised to the power of 10. This is a composition. The outer function is u to the power of 10, and the inner function is x squared plus 1. Using the chain rule, we first take the derivative of the outer function with respect to the inner function, which gives us 10 times x squared plus 1 to the power of 9. Then we multiply by the derivative of the inner function, which is 2x. So h prime of x equals 10 times x squared plus 1 to the power 9 times 2x, which simplifies to 20x times x squared plus 1 to the power 9. The chain rule shows up constantly in calculus. Anytime you have functions nested inside each other, you need the chain rule. It takes practice to recognize when to use it and to apply it correctly, but it becomes second nature with experience. Let's talk about derivatives of trigonometric functions. These are crucial because trig functions appear throughout mathematics and physics. The derivative of sine ax is cosine x. The derivative of cosine ax is negative sine ax. The derivative of tangent x is secant squared x. The derivative of cotangent x is negative cosecant squared x. The derivative of secant x is secant x tangent x. The derivative of cosecant x is negative cosecant x cotangent x. These might seem arbitrary, but they come from the limit definition of the derivative. For example, to find the derivative of sin x, we need the limit as h approaches 0 of sin x plus h minus sin x, all over h. Using trig identities and the fact that the limit as h approaches 0 of sin h over h equals 1, we can show this equals cosine x. You should verify these derivatives if you want to understand where they come from, but for practical purposes, you just need to memorize them. Combined with the chain rule, we can differentiate more complex trig functions. For example, the derivative of sine of x squared is cosine of x squared times 2x, which equals 2x cosine of x squared. The derivative of cosine of 3x is negative sine of 3x times 3, which equals negative 3 sine of 3x. Now let's discuss exponential and logarithmic functions. The exponential function e to the x has a remarkable property. Its derivative is itself. The derivative of e to the x is e to the x. This is one reason why e is so important in mathematics. It's the natural base for exponential functions. For exponentials with other bases, the derivative of a to the x is eta to the x times the natural log of a. But since e to the x is its own derivative, we usually convert other bases to base e when differentiating. Using the chain rule, the derivative of e to the u, where u is a function of x, is e to the u times u prime. So the derivative of e to the x squared is e to the x squared times 2x. The derivative of the natural logarithm, ln x, is 1 over x. This is another fundamental result. For logarithms with other bases, the derivative of log base a of x is 1 over x times ln a. But again, natural logarithms are most common. Using the chain rule, the derivative of ln of u is 1 over u times u prime. So the derivative of ln of x squared plus 1 is 1 over x squared plus 1 times 2x, which equals 2x over x squared plus 1. A useful technique called logarithmic differentiation can simplify finding derivatives of complicated products, quotients, or powers. The idea is to take the natural log of both sides of y equals f of x, use log properties to simplify, then differentiate implicitly. This is especially helpful for functions like y equals x to the x. Let's try that example. We have y equals x to the x. taking the natural log of both sides, ln y equals ln of x to the x, which by log properties equals x times ln x. Now we differentiate both sides with respect to x. The derivative of ln y with respect to x is 1 over y times di dx by the chain rule. The derivative of x ln x requires the product rule. 1 times ln x plus x times 1 over x, which equals ln x plus 1. So we have 1 over y times di dx equals ln x plus 1. Multiplying both sides by y, we get di dx equals y times ln x plus 1. Since y equals x to the x, we have di dx equals x to the x times ln x plus 1. Implicit differentiation is a technique for finding derivatives when you can't easily solve for y in terms of x. Sometimes equations define y implicitly as a function of x rather than explicitly. For example, the equation x squared plus y squared equals 25 describes a circle. We can't solve for y as a single function of x, but y is still a function of x along the circle. To differentiate implicitly, we differentiate both sides of the equation with respect to x, treating y as a function of x. For x squared plus y squared equals 25. Differentiating both sides gives 2x plus 2y times di dx equals 0. Notice we use the chain rule on y squared, which gives 2y times di dx. Now we solve for di dx. We get 2y times di dx equals negative 2x. So di dx equals negative x over y. This tells us the slope of the tangent line at any point on the circle. For example, at the point 3, 4, which is on the circle since 9 plus 16 equals 25, the slope is negative 3 over 4. Implicit differentiation is powerful because it works even when we can't solve for y explicitly. It's essential for many applications and will come up frequently in your calculus work. Higher-order derivatives are simply derivatives of derivatives. The second derivative, written as f double prime, or d squared f dx squared, is the derivative of the first derivative. The third derivative is the derivative of the second derivative, and so on. If f of x represents position, then f prime of x represents velocity, the rate of change of position, and f double prime of x represents acceleration, the rate of change of velocity. So higher-order derivatives have important physical interpretations. Let's compute some higher-order derivatives. If f of x equals x to the fourth, then f prime of x equals 4x cubed. The second derivative, f double prime of x, equals 12x squared. The third derivative equals 24x. The fourth derivative equals 24. The fifth derivative and all higher derivatives equal 0. Notice that for polynomials, eventually you get to 0 if you take enough derivatives. This is because each derivative reduces the degree by 1. For f of x equals e to the x, all derivatives are e to the x. This function is unchanged by differentiation. For f of x equals sine x, the first derivative is cosine x. The second derivative is negative sine x. The third derivative is negative cosine x. And the fourth derivative is sine x again. The derivatives cycle with period 4. The second derivative tells us about concavity. If f double prime is positive on an interval, the function is concave up, meaning it curves upward like a smile. If f double prime is negative, the function is concave down, meaning it curves downward like a frown. We'll explore this more in the next section when we discuss curve sketching. Let me emphasize the importance of practice with derivatives. The rules themselves are straightforward, but applying them correctly, especially the chain rule, requires practice. You need to be able to look at a function and immediately see its structure. Is it a product, quotient, composition, or combination? Then you apply the appropriate rules systematically. Common mistakes include forgetting the chain rule when you need it, mixing up the product, and quotient rules, and sign errors. Always double-check your work, especially with negative signs and fractions. The derivative is fundamentally about approximation. Near a point, a function looks approximately linear, and the derivative gives you that linear approximation. This idea of local linearity is central to calculus and has profound applications throughout mathematics and science. We've now covered the definition of the derivative, its interpretation as a slope and rate of change, all the major derivative rules, including power rule, product rule, quotient rule, and chain rule, derivatives of trigonometric, exponential, and logarithmic functions, implicit differentiation, and higher-order derivatives. These tools give you the power to differentiate essentially any function you'll encounter in Calculus Y. In the next section, we'll explore applications of derivatives, including related rates problems, optimization, and curve sketching. These applications show why derivatives are so useful and how they solve real-world problems. The derivative is not just an abstract mathematical concept, but a powerful tool for understanding change in every field of study. Now that we understand how to compute derivatives, let's explore how they're used to solve practical problems. This is where calculus really shines. The applications we'll discuss include related rates, optimization, curve sketching, and important theoretical results, like the mean value theorem. These techniques are used daily by scientists, engineers, economists, and mathematicians to solve real-world problems. Let's start with related rates problems. These are situations where multiple quantities are changing over time, and they're related to each other through some equation. We know the rate of change of one quantity and want to find the rate of change of another. The key is to use the chain rule, an implicit differentiation. Here's a classic example. Imagine a ladder 10 feet long leaning against a wall. The bottom of the ladder is sliding away from the wall at a rate of 2 feet per second. How fast is the top of the ladder sliding down the wall when the bottom is 6 feet from the wall? Let's set this up carefully. Let x be the distance from the wall to the bottom of the ladder, and let y be the height of the top of the ladder on the wall. We're told that dx dt, the rate at which x is changing, equals 2 feet per second. We want to find di dt when x equals 6. The relationship between x and y comes from the Pythagorean theorem. Since the ladder is 10 feet long, we have x squared plus y squared equals 100. Now we differentiate both sides with respect to time t. Using the chain rule, we get 2x times dx dt plus 2y times dy dt equals 0. We know x equals 6 and dx dt equals 2. We need to find y when x equals 6. From x squared plus y squared equals 100. We get 36 plus y squared equals 100. So y squared equals 64, meaning y equals 8. Now we plug everything into our differentiated equation. 2 times 6 times 2 plus 2 times 8 times di dat equals 0. That's 24 plus 16 times di dt equals 0. Solving for di dt, we get di dt equals negative 24 over 16, which equals negative 3/2 feet per second. The negative sign indicates the top is sliding down, which makes sense. Let's try another related rates problem. A spherical balloon is being inflated at a rate of 100 cubic centimeters per second. How fast is the radius increasing when the radius is 5 centimeters? The volume of a sphere is 4/3 πr cubed, where r is the radius. We're given dv dt equals 100, and we want dr dt when r equals 5. Differentiating the volume formula with respect to time, we get dv dt equals 4/3 pi times 3r squared times dr dt, which simplifies to 4 pi r squared times dr dt. This makes sense because 4 pi r squared is the surface area of the sphere. Plugging in our values, 100 equals 4 pi times 25 times Dr. dt. So 100 equals 100p times Dr. dt, giving us Dr. dt equals 1 over pi centimeters per second, approximately 0.32 centimeters per second. The general strategy for related rates problems is: first, draw a diagram if helpful and label all variables. Second, write an equation relating the variables. Third, differentiate both sides with respect to time using the chain rule. Fourth, substitute known values and solve for the unknown rate. Don't substitute values before differentiating, or you'll lose information. Now let's move to optimization problems. These involve finding maximum or minimum values of a function, often subject to some constraint. Optimization is everywhere in the real world. Businesses want to maximize profit or minimize cost. Engineers want to maximize strength or minimize weight, and so on. The key fact is that local maxima and minima occur at critical points. A critical point is where the derivative is zero or undefined. This makes intuitive sense. At a maximum or minimum, the function stops increasing and starts decreasing, or vice versa. At that turning point, the tangent line is horizontal, so the derivative is zero. However, not every critical point is a maximum or minimum. It could be what we call a saddle point, or inflection point. So we need tests to determine what type of critical point we have. The first derivative test uses the sign of the derivative on either side of a critical point. If the derivative changes from positive to negative, we have a local maximum. If it changes from negative to positive, we have a local minimum. If the derivative doesn't change sign, it's neither. The second derivative test uses the second derivative at the critical point. If the second derivative is positive, the function is concave up, so we have a local minimum. If the second derivative is negative, the function is concave down, so we have a local maximum. If the second derivative is zero, the test is inconclusive. Let's solve an optimization problem. We want to construct a rectangular box with a square base, an open top, and a volume of 32 cubic feet. What dimensions minimize the surface area? Let x be the side length of the square base and h be the height. The volume is x squared times h, which equals 32. So h equals 32 over x squared. The surface area includes the base and four sides, giving us a equals x squared plus 4xh. Substituting h equals 32 over x squared. We get a equals x squared plus 4x times 32 over x squared, which simplifies to x squared plus 128 over x. To minimize a, we take the derivative and set it equal to 0. dA dx equals 2x minus 128 over x squared. Setting this to 0, we get 2x equals 128 over x squared. Multiplying both sides by x squared, we get 2x cubed equals 128. So x cubed equals 64, meaning x equals 4. To verify this is a minimum, we can use the second derivative test. The second derivative is 2 plus 256 over x cubed. When x equals 4, this equals 2 plus 256 over 64, which equals 2 plus 4, which equals 6. Since this is positive, we have a minimum. When x equals 4, h equals 32 over 16, which equals 2. So the optimal dimensions are a 4-foot by 4-foot base with a height of 2 feet. Here's another classic optimization problem. You have 40 feet of fencing and want to enclose a rectangular area against a straight wall, so you only need fence for 3 sides. What dimensions maximize the enclosed area? Let x be the length of the side perpendicular to the wall and y be the length parallel to the wall. The fencing constraint is 2x plus y equals 40. So y equals 40 minus 2x. The area is A equals xy, which equals x times 40 minus 2x, giving us 40x minus 2x squared. Taking the derivative, dA dx equals 40 minus 4x. Setting this to 0, we get x equals 10. The second derivative is negative 4, which is negative, confirming this is a maximum. When x equals 10, y equals 20. So the optimal dimensions are 10 feet perpendicular to the wall and 20 feet parallel to the wall, giving a maximum area of 200 square feet. The general strategy for optimization problems is: first, identify what you're maximizing or minimizing and express it as a function. Second, if there are constraints, use them to eliminate variables until you have a function of one variable. Third, find critical points by taking the derivative and setting it equal to 0. Fourth, use the first or second derivative test to classify critical points. Fifth, check endpoints if the domain is restricted. The maximum or minimum on a closed interval could be at an endpoint rather than a critical point. Now, let's discuss curve sketching. Given a function, we want to understand its shape, where it's increasing or decreasing, where it has maxima or minima, where it's concave up or down, where it has inflection points, and what its asymptotes are. The derivative and second derivative give us all this information. A function is increasing where its derivative is positive and decreasing where its derivative is negative. Local maxima occur where the derivative changes from positive to negative. Local minima occur where the derivative changes from negative to positive. Points where the derivative is 0 or undefined are critical points and are candidates for local extrema. The second derivative tells us about concavity. Where the second derivative is positive, the function is concave up, curving like a smile. Where the second derivative is negative, the function is concave down, curving like a frown. An inflection point occurs where the concavity changes, meaning where the second derivative changes sign. Let's sketch the curve of f of x equals x cubed minus 3x squared minus 9, x plus 5. First, we find the derivative. F prime of x equals 3x squared minus 6x minus 9. Factoring, we get 3 times x squared minus 2x minus 3, which equals 3 times x minus 3 times x plus 1. So the critical points are at x equals 3 and x equals negative 1. To determine where the function is increasing or decreasing, we test the sign of f prime in the intervals determined by the critical points. For x less than negative 1, try x equals negative 2. F prime of negative 2 equals 3 times negative, 5 times negative 1, which is positive. For negative 1 less than x less than 3, try x equals 0. F prime of 0 equals 3 times negative, 3 times 1, which is negative. For x greater than 3, try x equals 4. F prime of 4 equals 3 times 1 times 5, which is positive. So the function is increasing on negative infinity to negative 1, decreasing on negative 1 to 3, and increasing on 3 to infinity. This means x equals negative 1 is a local maximum and x equals 3 is a local minimum. Now let's find the second derivative. F double prime of x equals 6x minus 6, which equals 6 times x minus 1. This is 0 when x equals 1. For x less than 1, f double prime is negative, so the function is concave down. For x greater than 1, f double prime is positive, so the function is concave up. Therefore, x equals 1 is an inflection point. We can evaluate the function at key points. F of negative 1 equals negative 1 minus 3 plus 9 plus 5 equals 10. F of 3 equals 27. minus 27, minus 27, plus 5 equals negative 22. F of 1 equals 1, minus 3 minus 9, plus 5 equals negative 6. Putting this all together, we know the function starts concave down and increasing, reaches a local maximum of 10 at x equals negative 1, then decreases while still concave down until the inflection point at x equals 1, where y equals negative 6. Then continues decreasing but now concave up until the local minimum of negative 22 at x equals 3, then increases and is concave up forever. For rational functions, we also need to identify vertical and horizontal asymptotes. Vertical asymptotes occur where the denominator is 0, but the numerator isn't. Horizontal asymptotes describe the behavior as x approaches infinity or negative infinity, which we determine using limits. Consider f of x equals 2x squared minus x plus 1, all over x squared minus 4. The denominator factors as x minus 2 times x plus 2, so there are vertical asymptotes at x equals 2 and x equals negative 2. For the horizontal asymptote, we look at the limit as x approaches infinity. Dividing numerator and denominator by x squared, we get 2 minus 1 over x plus 1 over x squared, all over 1 minus 4 over x squared. As x approaches infinity, the terms with x in the denominator approach 0, leaving 2 over 1, which equals 2. So y equals 2 is a horizontal asymptote. To find the derivative, we use the quotient rule. F prime of x equals 4, x minus 1 times x, squared, minus 4, minus 2, x squared minus x plus 1 times 2x, all over x squared minus 4 squared. This simplifies to negative 6x squared plus 8x minus 4, all over x squared minus 4 squared. Setting the numerator equal to 0 and solving gives us the critical points. The mean value theorem is one of the most important theoretical results about derivatives. It says that if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists some c in the interval where f prime of a seguido equals f of b minus ffe of a all over b minus a. In other words, there's at least one point where the instantaneous rate of change, the derivative, equals the average rate of change over the interval. Geometrically, this means there's a point where the tangent line is parallel to the secant line connecting the endpoints. This might seem like an abstract result, but it has important consequences. For example, it implies that if the derivative is 0 everywhere on an interval, then the function is constant on that interval. If two functions have the same derivative on an interval, they differ by at most a constant. The mean value theorem is used to prove many other results in calculus. It's the theoretical foundation for much of what we do with derivatives. While you might not use it directly to solve problems, understanding it deepens your comprehension of how derivatives work. Rolle's theorem is a special case of the mean value theorem. It says that if AF is continuous on a closed interval from a to b, differentiable on the open interval, and f of a equals f of b, then there exists some c where f prime of c high equals 0. In other words, if a function starts and ends at the same height, there must be a horizontal tangent somewhere in between. Let's apply these concepts to a physics problem. Suppose a car travels from point A to point B, a distance of 100 miles, in 2 hours. At some point during the trip, the car must have been traveling at exactly 50 miles per hour. Why? Because the average velocity is 100 miles divided by 2 hours, which equals 50 miles per hour. The mean value theorem guarantees that the instantaneous velocity, the derivative of position with respect to time, must equal the average velocity at some moment. This has practical implications. If you're caught speeding, you can't argue that your average speed was below the limit. At some instant, You are going the speed indicated by your instantaneous velocity. L'Hopital's rule is a powerful technique for evaluating limits that give indeterminate forms, like 0 over 0 or infinity over infinity. If the limit as x approaches a of f of x over g of x gives 0 over 0 or infinity over infinity, then this limit equals the limit as x approaches ai of f prime of x over g prime of x, provided this second limit exists. For example, consider the limit as x approaches 0 of sin x over x. Direct substitution gives 0 over 0. Using L'Hopital's rule, we take the derivative of the numerator and denominator separately, giving us the limit as x approaches 0 of cosine x over 1, which equals 1. This confirms a result we mentioned earlier. Another example, the limit as x approaches infinity of x over e to the x. This gives infinity over infinity. Applying L'Hopital's rule, we get the limit as x approaches infinity of 1 over e to the x, which equals 0. So exponential growth dominates polynomial growth. Sometimes you need to apply L'Hopital's rule multiple times. Consider the limit as x approaches 0 of 1 minus cosine x, all over x squared. This gives 0 over 0. Applying L'Hopital's rule, we get the limit as x approaches 0 of sin ex over 2x. This still gives 0 over 0, so we apply L'Hopital's rule again, getting the limit as x approaches 0 of cosine x over 2, which equals 1/2. Be careful with L'Hopital's rule. It only applies to indeterminate forms. If the limit doesn't give 0 over 0 or infinity over infinity, you can't use L'Hopital's rule. Also, you take the derivative of the numerator and denominator separately, not the derivative of the quotient. It's not the quotient rule. Linear approximation is another application of derivatives. Near a point, a function is approximately linear, and the tangent line gives that linear approximation. If we want to approximate f of a plus h for small h, we can use f of a plus f prime of a times h. This is called the linear approximation, or tangent line approximation. For example, let's approximate the square root of 66. We know the square root of 64 is 8. Let f of x equal the square root of x. So f of 64 equals 8. The derivative is 1 over 2 times the square root of x. So f prime of 64 equals 1 over 16. Using the linear approximation, the square root of 66 is approximately 8 plus 1/16 times 2, which equals 8 plus 1/8, which equals 8.125. The actual value is about 8.124, so our approximation is quite good. This technique is useful for mental calculations and understanding how functions behave locally. It's also the basis for more sophisticated approximation methods like Newton's method for finding roots of equations. Newton's method is an iterative algorithm for finding where a function equals 0. The idea is to start with an initial guess, use the tangent line to get a better guess, and repeat. Specifically, if xn is our current guess, the next guess is xn plus 1 equals xn minus f of xn over f prime of xn. For example, to find the square root of 2, we solve x squared minus 2 equals 0. Let's f of x equal x squared minus 2, so f prime of x equals 2, x. Starting with x0 equals 1, we get x1 equals 1 minus negative 1 over 2, which equals 1.5. Then x2 equals 1.5 minus 0.25 over 3, which equals 1.4167. Then x3 equals 1.4167 minus approximately 0.0069 over 2.83, which equals approximately 1.4142. This converges rapidly to the square root of 2, which is about 1.4142. Newton's method is powerful, but requires a good initial guess and a well-behaved function. It can fail if the derivative is zero, or if the function has unusual behavior, but when it works, it converges very quickly. Marginal analysis in economics is another important application of derivatives. The marginal cost is the derivative of the cost function, representing the cost of producing one additional unit. The marginal revenue is the derivative of the revenue function. Profit is maximized where marginal cost equals marginal revenue. Suppose the cost to produce X units is C of X equals 100 plus 5, X plus 0.01 X squared, and the revenue is R of X equals 20X. The profit is P of X equals R of X minus C of X, which equals 20X minus 100 minus 5, X minus 0.01 X squared. Simplifying to negative 100 plus 15 X minus 0.01 X squared. To maximize profit, we take the derivative. P prime of X equals 15 minus 0.02 X. Setting this to 0, we get X equals 750. We can verify this is a maximum using the second derivative test. P double prime of X equals negative 0.02, which is negative, confirming a maximum. So the optimal production level is 750 units. Exponential growth and decay are modeled using differential equations involving derivatives. If a quantity grows or decays at a rate proportional to its current amount, we have di dt equals k or y, where k is the growth or decay constant. The solution is y equals y0 times e to the kt, where y0 is the initial amount. This models population growth, radioactive decay, compound interest, cooling of objects, and many other phenomena. For example, if a population grows at 3% per year, after t years the population is p0 times e to the 0.03t, where p0 is the initial population. Related to this is the concept of half-life for radioactive decay. The half-life is the time it takes for half the substance to decay. If the decay constant is k, the half-life is the natural log of 2 divided by k. We've now covered a wide range of applications. Related rates problems where multiple quantities change over time. Optimization problems where we find maximum or minimum values. Curve sketching where we use derivatives to understand the shape of graphs. The mean value theorem and its implications. L'Hopital's rule for evaluating limits. Linear approximation and Newton's method, and applications to economics and exponential models. These applications demonstrate the power and versatility of derivatives. The derivative is not just a mathematical abstraction, but a practical tool for solving problems in every scientific and technical field. Whether you're an engineer designing a bridge, an economist analyzing markets, a biologist modeling populations, or a physicist describing motion, you'll use derivatives constantly. The key to mastering applications is practice. Work through many problems, understand the general strategies, and learn to translate word problems into mathematical equations. With experience, you'll develop intuition for how to approach different types of problems and which techniques to apply. In the next section, we'll turn to integration, the other fundamental operation of calculus. While derivatives measure rates of change, integrals measure accumulation. Together, derivatives and integrals form a complete picture of how we analyze functions using calculus. We now turn to the second major branch of calculus, integration. If differentiation is about taking things apart, understanding instantaneous rates of change, then integration is about putting things together, understanding accumulation. These two operations are intimately connected, as we'll see through the fundamental theorem of calculus, one of the most beautiful results in all of mathematics. Let's start with a motivating question. Suppose you're driving a car and you know your velocity at every moment. Can you figure out how far you've traveled? If your velocity is constant, this is easy. Distance equals velocity times time. But what if your velocity is changing? What if you're accelerating or decelerating? This is where integration comes in. Think about it this way. If your velocity is changing, you could approximate the distance by breaking the time into small intervals. During each small interval, you could pretend the velocity is constant and use distance equals velocity times time for that interval. Then you add up all these small distances. The smaller you make the intervals, the better your approximation. In the limit, as the intervals become infinitesimally small, you get the exact distance. This process of adding up infinitely many infinitesimal pieces is integration. The same idea applies to many other situations. If you know the rate at which water is flowing into a tank, integration tells you the total amount of water. If you know the rate at which a population is growing, integration tells you the population change. If you know the density of a rod at each point, integration tells you the total mass. Integration is fundamentally about accumulation. Let's make this more precise. An antiderivative of a function f is a function f whose derivative is f. In other words, f prime equals f. For example, an antiderivative of 2x is x squared, because the derivative of x squared is 2x. An antiderivative of cosine x is sine x, because the derivative of sine x is cosine x. Notice I said an antiderivative, not the antiderivative. That's because antiderivatives are not unique. If f is an antiderivative of f, then so is f plus any constant c. The derivative of a constant is 0, so adding a constant doesn't change the derivative. Therefore, the most general antiderivative of f is f plus c, where c is an arbitrary constant. We write the indefinite integral of f of x as the integral sign f of x dx. This notation means find all antiderivatives of f. The result is always a family of functions differing by a constant. So the integral of 2x dx equals x squared plus c. The integral of cosine x dx equals sine x plus c. The dx at the end is not just decoration. It indicates that we're integrating with respect to x. It also reminds us of the limiting process behind integration, where dx represents an infinitesimally small change in x. Finding antiderivatives is essentially the reverse of finding derivatives, but it's generally harder. With derivatives, we have systematic rules that always work. With antiderivatives, we need various techniques, and some functions don't have antiderivatives that can be expressed in terms of elementary functions. Let's establish some basic integration formulas by reversing our derivative rules. The integral of x to the n dx equals x to the n plus 1, divided by n plus 1 plus c, provided n is not equal to -1. This is the reverse of the power rule for derivatives. So the integral of x cubed dx equals x to the 4th over 4 plus c. The integral of x to the 1/2 dx equals x to the 3/2 divided by 3/2, which equals 2/3. X to the 3/2 plus c. The case n equals -1 is special. The integral of 1 over x dx, which is x to the -1, doesn't fit the power rule formula. Instead, the integral of 1 over x dx equals the natural log of the absolute value of x plus c. We need the absolute value because the natural log is only defined for positive arguments, but 1 over x is defined for all non-zero x. The integral of e to the x dx equals e to the x plus c, since the derivative of e to the x is itself. The integral of a to the x dx equals a to the x divided by the natural log of a plus c. For trigonometric functions, the integral of sine x dx equals negative cosine. x plus c. The integral of cosine x dx equals sine x plus c. The integral of secant squared x dx equals tangent x plus c. The integral of secant x tangent x dx equals secant x plus c. The integral of 1 over the square root of 1 minus x squared dx equals RC arcsine x plus c. The integral of 1 over 1 plus x squared dx equals arctangent x plus c. These formulas should be memorized, just like derivative formulas. They're the building blocks for more complicated integrals. Integration has linear properties, just like differentiation. The integral of a sum is the sum of the integrals. The integral of a constant times a function is the constant times the integral of the function. So to integrate 3x squared minus 4x plus 5, we integrate term by term. 3 times x cubed over 3 minus 4 times x squared over 2 plus 5x, which simplifies to x cubed minus 2x squared plus 5x plus c. Now let's discuss the definite integral, which is a number rather than a function. The definite integral from a to b of f of x dx represents the signed area between the curve y equals f of x and the x-axis, from x equals a to x equals b. I say signed area because area above the x-axis is positive and area below the x-axis is negative. To understand this geometrically, imagine we want to find the area under the curve. Y equals x squared, from x equals 0 to x equals 1. We can approximate this by dividing the interval from 0 to 1 into n equal subintervals, each of width delta x equals 1 over n. In each subinterval, we construct a rectangle, whose height is the value of the function at some point in that subinterval. The area of each rectangle is height times width, which is f of xi times delta x. We add up all these rectangular areas to get an approximation of the total area. This sum is called a Riemann sum. As we increase n, making the rectangles narrower, the approximation gets better. In the limit as n approaches infinity, the Riemann sum approaches the exact area. This limit is the definite integral. Formally, the definite integral from a to b of f of x dx is the limit as n approaches infinity of the sum from I equals 1 to n of f of xi times delta x, where the interval is divided into n subintervals and xi is a point in the ith subinterval. There are different types of Riemann sums depending on where we evaluate the function in each subinterval. If we use the left endpoint, it's a left Riemann sum. If we use the right endpoint, it's a right Riemann sum. If we use the midpoint, it's a midpoint Riemann sum. In the limit, they all give the same value, the definite integral, provided the function is reasonably well behaved. Let's compute a Riemann sum for a specific example. Consider the integral from 0 to 2 of x squared dx. Let's use 4 subintervals, so delta x equals 2 over 4, which equals 1/2. Using left endpoints, we evaluate the function at 0, 1/2, 1, and 3/2. At x equals 0, f of x equals 0. At x equals 1/2, f of x equals 1/4. At x equals 1, f of x equals 1. At x equals 3/2, f of x equals 9/4. The left Riemann sum is 0 times 1/2 plus 1/4 times 1/2 plus 1 times 1/2 plus 9/4 times 1/2, which equals 0 plus 1/8 plus 1/2 plus 9/8, which equals 14/8, or 7/4. Using right endpoints at 1/2, 1, 3/2, and 2, we get 1/4 times 1/2 plus 1 times 1/2 plus 9/4 times 1/2 plus 4 times 1/2, which equals 1/8 plus 1/2 plus 9/8 plus 2, which equals 38 over 8, or 15/4. The left sum underestimates and the right sum overestimates because the function is increasing. The true value of the integral is between these, and as we increase the number of subintervals, both converge to the exact value. The definite integral has several important properties. The integral from a to b of f of x dx equals negative 1 times the integral from b to a of f of x dx. Reversing the limits changes the sign. The integral from a to a of f of x dx equals 0. The integral from a to b plus the integral from b to c equals the integral from a to c. This is the additive property. Integrating over two adjacent intervals is the same as integrating over the combined interval. If f of x is less than or equal to g of x on the interval from a to b, then the integral from a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. This comparison property makes intuitive sense. If one curve is always below another, its signed area is less. The average value of a function f on the interval from a to b is defined as 1 over b minus a times the integral from a to b of f of x dx. This is like the mean of all the function values over the interval. For example, if you want the average temperature over a day, you integrate the temperature function over 24 hours and divide by 24. Now we come to the fundamental theorem of calculus, which connects differentiation and integration. This theorem has two parts, and together they're among the most important results in mathematics. The first fundamental theorem of calculus says that if EF is continuous on an interval, and f is defined as the integral from a to x of f of t, then f is differentiable and f prime of x equals f of x. In other words, if you integrate a function, then differentiate the result, you get back the original function. Integration and differentiation are inverse operations. This is profound. It means that the integral function, defined as an accumulation of area, is an antiderivative. The rate of change of the accumulated area is the height of the function. If you think about it geometrically, this makes sense. As x increases by a tiny amount dx, the additional area is approximately the height f of x times the width dx, so the rate of change of area with respect to x is f of x. The second fundamental theorem of calculus says that if f is any antiderivative of f, then the integral from a to b of f of x dx equals f of b minus f of a. This gives us a practical way to evaluate definite integrals. Instead of computing limits of Riemann sums, we can find any antiderivative f, evaluate it at the endpoints, and subtract. We typically write f of b minus f of a is f of x evaluated from x equals a to x equals b, using a vertical bar notation. For example, the integral from 0 to 2 of x squared dx equals x cubed over 3, evaluated from 0 to 2, which equals 8/3 minus 0, which equals 8/3. Let's verify this matches our intuition from the Riemann sums. We estimated the value was between 7/4 and 15/4, which is between 1.75 and 3.75. Our exact answer is 8/3, which is approximately 2.67, indeed in that range. With more subintervals, the Riemann sums would converge to 8/3. The fundamental theorem is why we study antiderivatives. To evaluate a definite integral, we need an antiderivative. This connects the two branches of calculus. Derivatives measure instantaneous change. Integrals measure total accumulation. And the fundamental theorem says these are inverse operations. Let's work through more examples. The integral from 1 to 3 of v, 2x plus 1 dx. The antiderivative is x squared plus x. Evaluating at 3 gives 9 plus 3 equals 12. Evaluating at 1 gives 1 plus 1 equals 2. Subtracting, we get 12 minus 2 equals 10. The integral from 0 to pi of sine x dx equals negative cosine. x evaluated from 0 to pi. At pi, negative cosine pi equals negative times negative 1 equals 1. At 0, negative cosine 0 equals negative 1. So the answer is 1 minus negative 1, which equals 2. The integral from 1 to e of 1 over x dx equals the natural log of the absolute value of x, evaluated from 1 to e. Since these are positive values, we can drop the absolute value. Natural log of e is 1. Natural log of 1 is 0. So the answer is 1 minus 0, which equals 1. Notice that we don't include the plus c when evaluating definite integrals. The constant cancels when we subtract f. Of b minus f. Of a, the plus c is only necessary for indefinite integrals, where we want the most general antiderivative. Let's consider a motion problem. Suppose the velocity of an object is v of t equals 3 times t squared minus 2 t plus 1 meters per second. What is the displacement from t car t equals 0 to t equals 3 seconds? Displacement is the integral of velocity. The integral from 0 to 3 of 3t squared minus 2 to t plus 1 dt equals t cubed minus t squared plus t, evaluated from 0 to 3. At t equals 3, we get 27 minus 9 plus 3 equals 21. At t equals 0, we get 0. So the displacement is 21 meters. What about the total distance traveled? That's different from displacement if the object changes direction. We need to check if the velocity changes sign. Setting 3t squared minus 2t plus 1 equal to 0, and using the quadratic formula, the discriminant is 4 minus 12 equals negative 8, which is negative. So there are no real roots, meaning the velocity never equals 0. Since v of 0 equals 1, which is positive, the velocity is always positive. Therefore, the object never changes direction, and the total distance equals the displacement, 21 meters. If the velocity had changed sign, we'd need to integrate the absolute value of velocity, which requires breaking the integral into pieces where the velocity is positive and negative separately. The area interpretation of integrals is important, but not the whole story. Integrals compute many things: area, volume, arc length, work, probability, and more. The key is always setting up the right integral for the quantity you want to compute. For area, if f of x is greater than or equal to 0 on the interval from a to b, then the integral from a to b of f of x dx gives the area between the curve and the x-axis. If f of x is less than or equal to 0, the integral is negative, and the area is the absolute value of the integral. If f changes sign, you need to integrate separately over intervals where it's positive and negative, taking absolute values. To find the area between two curves, y equals f of x and y equals g of x, from x equals a to x equals b, where f of x is greater than or equal to g of x. The area is the integral from a to b of f of x minus g of x dx. You integrate the top function minus the bottom function. This makes sense because you're subtracting the lower area from the higher area. Let's find the area between y equals x squared and y equals x, from x equals 0 to x equals 1. Which function is on top? At x equals 1/2, x squared equals 1/4 and x equals 1/2, so x is greater. In fact, x is greater than x squared throughout this interval, so we integrate x minus x squared. The integral from 0 to 1 of x minus x squared dx equals x squared over 2 minus x cubed over 3, evaluated from 0 to 1. At x equals 1, we get 1/2 minus 1/3 equals 3/6 minus 2/6 equals 1/6. At x equals 0, we get 0. So the area is 1/6 square units. For areas with respect to the y-axis, we integrate with respect to y instead of x. If x is expressed as a function of y, say x equals h of y, then the area between the curve and the y-axis from y equals c to y equals d is the integral from c to d of h of y dy. Substitution is the first major technique for finding antiderivatives. It's the reverse of the chain rule. If you have an integral that looks like the integral of f of g of x times g prime of x dx, you can substitute u equals g of x, so du equals g prime of x dx, transforming the integral into the integral of f of u du. For example, consider the integral of 2x and times x squared plus 1 to the fifth dx. Let u equal x squared plus 1, so du equals 2x dx. The integral becomes the integral of u to the fifth du, which equals u to the sixth over 6 plus c. Substituting back, we get x squared plus 1 to the sixth divided by 6 plus c. The key is recognizing when a substitution will work. You need the derivative of the inside function to appear as a factor, possibly with a constant multiple. Sometimes you need to manipulate the integrand to make the substitution work. Let's try another. The integral of sine cubed x cosine x dx. Let u equal sin xi, so du equals cosine x dx. The integral becomes the integral of u cubed du, which equals u to the fourth over 4 plus c. Substituting back, we get sin a to the fourth x over 4 plus c. For definite integrals, when you substitute, you should also change the limits of integration. If the integral is from x equals a to x equals b, and you substitute u equals g of x, the new limits are u equals g of a to u equals g of b. Then you integrate with respect to u between these new limits and don't need to substitute back to x. For example, the integral from 0 to 1 of x times the square root of 1 plus x squared dx. Let u equal 1 plus x squared, so du equals 2x dx, meaning x dx equals 1/2 du. When x equals 0, u equals 1. When x equals 1, u equals 2. The integral becomes the integral from 1 to 2 of the square root of u times 1/2 du, which equals 1/2 times 2/3 u to the 3/2. Evaluated from 1 to 2. That's 1/3 times 2 to the 3/2 minus 1, which equals 1/3 times 2 times the square root of 2 minus 1. Integration by parts is another important technique. It's the reverse of the product rule. The formula is the integral of u dv equals uv minus the integral of v du. The idea is to choose u and dv from your integrand, such that the integral of v du is easier than the original integral. For example, consider the integral of x times e to the x dx. Let u equal x, so du equals dx. Let dv equal e to the x dx, so v equals e to the x. Using integration by parts, the integral equals x times e to the x minus the integral of e to the x dx, which equals xe to the x minus e, to the x plus c, which factors as e to the x times x minus 1 plus c. Choosing u and dv takes practice. A common heuristic is Lie8, logarithmic, inverse trig, algebraic, trigonometric, exponential. Choose u in that priority order. For xe to the x is algebraic, and e to the x is exponential, so we chose u equals x. Sometimes you need to use integration by parts multiple times. For the integral of x squared e to the x dx, you'd apply integration by parts twice, each time reducing the power of x. Occasionally, integration by parts leads to an equation involving the original integral. For the integral of e to the x sine x dx, after applying integration by parts twice, you get an equation like I equals something minus I, which you can solve for I. The techniques of integration are vast. Beyond substitution and integration by parts, there are methods for trigonometric integrals, trigonometric substitution, partial fractions, and more. Some of these are typically covered in Calculus 2. For Calculus 1, mastering basic antiderivatives, substitution, and understanding the fundamental theorem are the priorities. Let me emphasize the importance of checking your work. After finding an antiderivative, you can always check by differentiating. If you claim the integral of f of x dx is f of x plus c, compute f prime of x. If you get f of x, you're correct. This is a valuable habit and catches many errors. Integration is harder than differentiation because there's no single algorithm that always works. Some functions don't have antiderivatives expressible in elementary functions. For example, the integral of e to the x squared dx cannot be written in terms of familiar functions, even though the integrand is simple. This is surprising but true. However, definite integrals of such functions can still be approximated numerically. In the next section, we'll explore more integration techniques and applications, including areas, volumes, and basic differential equations. We'll see how integration solves real-world problems in physics, engineering, and other fields. Integration, like differentiation, is a powerful tool that extends far beyond the classroom. We now explore more sophisticated integration techniques and delve deeper into applications. Integration is remarkably versatile, solving problems involving area, volume, work, and much more. The techniques we'll discuss give you the tools to tackle a wide range of integrals, though mastering them requires substantial practice. Let's start by expanding our repertoire of integration techniques. We've already covered basic antiderivatives and substitution. Now we'll explore more advanced substitution strategies and other methods that appear in Calculus Y. Sometimes an integral requires clever algebraic manipulation before substitution becomes apparent. Consider the integral of 1 over x times the natural log of x dx. This looks complicated, but if we let u equal the natural log of x, then du equals 1 over x dx. The integral becomes the integral of 1 over u du, which equals the natural log of the absolute value of u plus c. Substituting back, we get the natural log of the absolute value of the natural log of x plus c. This is a composition of logarithms, which might seem strange, but it's perfectly valid. For trigonometric integrals, there are several useful strategies. When integrating powers of sine and cosine, if one has an odd power, factor out one copy and use the Pythagorean identity sine squared plus cosine squared equals 1 to convert the rest. For example, the integral of sine cubed x dx equals the integral of sine squared x times sine x dx, which equals the integral of 1 minus cosine squared x times sine x dx. Let u equal cosine x, so du equals negative sine x dx. The integral becomes the integral of 1 minus u squared times negative du, which equals the integral of u squared minus 1 du, giving u cubed over 3 minus u plus c. Substituting back, we get cosine cubed x over 3 minus cosine x plus c. If both sine and cosine have even powers, you use power-reducing formulas derived from double angle identities. Sine squared x equals 1 minus cosine 2x all over 2. Cosine squared x equals 1 plus cosine 2x all over 2. For the integral of sine squared x dx, we write this as the integral of 1 minus cosine 2x over 2 dx, which equals 1/2 times x minus sine 2x over 2 plus c, simplifying 2x over 2 minus sine 2x over 4 plus c. For integrals involving tangent and secant, similar strategies apply. If the integrand contains secant squared, factor it out for substitution with tangent. If it contains secant tangent, factor those out for substitution with secant. The integral of tangent squared x dx might not look obvious, but we can rewrite tangent squared as secant squared minus 1 using the Pythagorean identity. So the integral becomes the integral of secant squared x minus 1 bx, which equals tangent x minus s x plus c. Trigonometric substitution is a powerful technique for integrals involving square roots of quadratic expressions. If you see the square root of a squared minus x squared, substitute x equals a sin theta. If you see the square root of a squared plus x squared, substitute x equals a tangent theta. If you see the square root of x squared minus a squared, substitute x equals a secant theta. These substitutions use Pythagorean identities to eliminate the square root. Let's work an example. Consider the integral of 1 over the square root of 4 minus x squared dx. We have the square root of 2 squared minus x squared, so substitute x equals 2 sine theta, giving dx equals 2 cosine theta d theta. The square root becomes the square root of 4 minus 4 sine squared theta, which equals the square root of 4 times 1 minus sine squared theta, which equals 2 times the square root of cosine squared theta, which equals 2 cosine theta, since we choose the positive root in the appropriate range. The integral becomes the integral of 2 cosine theta over 2 cosine theta d theta, which simplifies to the integral of 1 d theta, which equals theta plus c. Now, we need to express theta in terms of x. Since x equals 2 sin theta, we have sin theta equals x over 2, so theta equals arcsine of x over 2. Therefore, the integral equals arcsine of x over 2 plus c. This technique transforms seemingly difficult integrals into manageable trigonometric integrals. The challenge is recognizing when to use it and correctly handling the substitution and back substitution. Partial fractions is a technique for integrating rational functions, where the numerator and denominator are polynomials. The idea is to decompose the rational function into simpler fractions that we can integrate individually. This is typically a Calculus 2 topic in full generality, but basic cases appear in Calculus 1 more. If the degree of the numerator is greater than or equal to the degree of the denominator, first perform polynomial long division. Then you're left with a proper rational function where the numerator has lower degree than the denominator. For the denominator, factor it completely. For each linear factor of the form x minus a, there's a term a over x minus a in the partial fraction decomposition. For each irreducible quadratic factor, there's a term of the form bx plus c over the quadratic. Consider the integral of 1 over x squared minus 1 dx. Factor the denominator as x minus 1 times x plus 1. The partial fraction decomposition is a over x minus 1 plus b over x plus 1. Multiplying through by the denominator, we get 1 equals a times x plus 1 plus b times x minus 1. Setting x equals 1 gives 2a equals 1, so a equals 1 half. Setting x equals negative 1 gives negative 2b equals 1, so b equals negative 1 half. Therefore, the integral equals 1 half times the integral of 1 over x minus 1 dx minus 1 half times the integral of 1 over x plus 1 dx, which equals 1 half times the natural log of the absolute value of x minus 1 minus 1, half times the natural log of the absolute value of x plus 1 plus c. This can be written as 1 half times the natural log of the absolute value of x minus 1 over x plus 1 plus c. Improper integrals extend the concept of definite integrals to infinite intervals or integrands with infinite discontinuities. These require limits. For the integral from a to infinity of f of x dx, we define this as the limit as b approaches infinity of the integral from a to b of f of x dx. If this limit exists and is finite, the improper integral converges. Otherwise, it diverges. For example, the integral from 1 to infinity of 1 over x squared dx equals the limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. The antiderivative is negative 1 over x. Evaluating, we get the limit as b approaches infinity of negative 1 over b minus negative 1 over 1. As b approaches infinity, negative 1 over b approaches 0, so the limit is 0 minus negative 1 equals 1. This improper integral converges to 1. Contrast this with the integral from 1 to infinity of 1 over x dx, which equals the limit as b approaches infinity of the natural log of x evaluated from 1 to b. This equals the limit as b approaches infinity of natural log of b minus natural log of 1. Natural log of 1 is 0, but natural log of b approaches infinity as b approaches infinity. So this improper integral diverges. These examples show that 1 over x squared decreases fast enough for the area to be finite, but 1 over x does not. This distinction is important in many applications, particularly in physics and probability theory. If the integrand has a vertical asymptote at x equals c within the interval from a to b, we split the integral at c and evaluate as limits from both sides. For the integral from 0 to 1 of 1 over the square root of x dx, there's a vertical asymptote at x equals 0. We write this as the limit as t approaches 0 from the right of the integral from t to 1 of 1 over the square root of x dx. The antiderivative is 2 times the square root of x. Evaluating, we get the limit as t approaches 0 from the right of 2 times the square root of 1 minus 2 times the square root of t, which equals 2 minus 0 equals 2. This improper integral converges to 2. Now let's turn to applications of integration beyond area. One of the most important is finding volumes of solids. There are several methods, including the disk method, washer method, and shell method. The disk method applies when a solid is formed by rotating a region around an axis. If we rotate the region under y equals f of x from x equals a to x equals b around the x-axis, the volume is the integral from a to b of pi times f of x squared dx. The idea is that each cross-section perpendicular to the x-axis is a disk with radius f of x, so area pi times f of x squared. Integrating these areas gives the volume. For example, let's find the volume when the region under y equals the square root of x from x equals 0 to x equals 4 is rotated around the x-axis. The volume is the integral from 0 to 4 of pi times the square root of x squared dx, which equals the integral from 0 to 4 of pi x dx. This equals pi times x squared over 2, evaluated from 0 to 4, which equals pi times 8, or 8 pi cubic units. The washer method is similar, but applies when there's a hole in the solid. If we rotate the region between y equals f of x and y equals g of x, where f is above g, around the x-axis, each cross-section is a washer with outer radius f of x and inner radius g of x. The area of the washer is pi times f of x squared minus pi times g of x squared. The volume is the integral from a to b of pi times f of x squared minus g of x squared dx. Let's find the volume when the region between y equals x and y equals x squared, from x equals 0 to x equals 1 is rotated around the x-axis. The outer radius is x and the inner radius is x squared. The volume is the integral from 0 to 1 of pi times x squared minus x to the fourth dx, which equals pi times x cubed over 3 minus x to the fifth over 5, evaluated from 0 to 1. This equals pi times 1/3 minus 1/5, which equals pi times 5/15 minus 3/15, which equals 2 pi over 15 cubic units. The shell method uses a different approach. When rotating around a vertical axis, Instead of slicing horizontally, we slice vertically into cylindrical shells. If we rotate the region under y equals f of x, from x equals a to x equals b around the y-sum axis, the volume is the integral from a to b of 2 pi x times f of x dx. Each shell has radius x, height f of x, and thickness dx. The surface area is 2 pi x times f of x, and multiplying by thickness gives the volume element. For example, rotating the region under y equals x squared, from x equals 0 to x equals 2. Around the y-axis gives volume equal to the integral from 0 to 2 of 2 pi x times x squared dx, which equals the integral from 0 to 2 of 2 pi x cubed dx. This equals 2 pi times x to the 4th over 4, evaluated from 0 to 2, which equals pi times 16 over 2, which equals 8 pi cubic units. Choosing between disk and shell methods often depends on which gives a simpler integral. Sometimes one method requires difficult manipulations, while the other is straightforward. Developing intuition for which method to use comes with practice. Arc length is another geometric application of integration. The length of a curve y equals f of x from x equals a to x equals b is given by the integral from a to b of the square root of 1 plus f prime of x squared dx. This formula comes from approximating the curve by many short line segments and using the Pythagorean theorem. The length of each segment is approximately the square root of dx squared plus dy squared, which equals the square root of 1 plus di over dx squared times dx. Let's find the arc length of y equals x to the 3 halves, from x equals 0 to x equals 4. First, di over dx equals 3 halves, times x to the 1 half. So 1 plus di over dx squared equals 1 plus 9/4 x. The arc length is the integral from 0 to 4 of the square root of 1 plus 9/4 x dx. Let u equal 1 plus 9/4 x. So do equals 9/4 dx, meaning dx equals 4/9 du. When x equals 0, u equals 1. When x equals 4, u equals 10. The integral becomes the integral from 1 to 10 of the square root of u times 4/9 du, which equals 4/9 times 2/3 u to the 3 halves, evaluated from 1 to 10. This equals 8 over 27 times 10 to the 3 halves minus 1, which equals 8 over 27 times 10 times the square root of 10 minus 1. Surface area of revolution is similar. If we rotate the curve y equals f of x from x equals a to x equals b around the x-axis, the surface area is the integral from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx. The idea is that each small piece of the curve, when rotated, forms a band around the surface. The circumference is 2 pi f of x. The width is the arc length element, so the area is their product. Work is an important application in physics. Work is force times distance, but when force varies with position, we need integration. If an object moves from x equals a to x equals b under a force f of x, the work done is the integral from a to b of f of x dx. For example, Hooke's law says the force required to stretch or compress a spring is proportional to the displacement. If f of x equals k/x, where k is the spring constant, the work to stretch the spring from its natural length to a distance d is the integral from 0 to d of kx dx, which equals ka times x squared over 2, evaluated from 0 to d, giving kd squared over 2. Suppose a spring has spring constant 20 newtons per meter. How much work is required to stretch it from 0.1 meters to 0.3 meters? The work is the integral from 0.1 to 0.3 of 20x dx, which equals 10 times x squared, evaluated from 0.1 to 0.3. This equals 10 times 0.09 minus 0.01, which equals 10 times 0.08, which equals 0.8 joules. Pumping liquids out of tanks is another work application. The weight of liquid at depth y must be lifted a certain distance. The total work is the integral of weight times distance over all depths. These problems require setting up the integral carefully, considering the geometry of the tank and how far each layer of liquid must be lifted. Center of mass and moments involve integration when dealing with continuous distributions. For a thin rod along the x-axis, from x equals a to x equals b, with density function Rho of x, the mass is the integral from a to b of Rho of x dx. The moment about the origin is the integral from a to b of x times Rho of x dx. The center of mass is the moment divided by the mass. For two-dimensional regions, similar formulas apply, but with double integrals, which are typically covered in Calculus 3. However, for regions bounded by curves in the plane, using symmetry and single integrals can sometimes suffice. Average value of a function, which we mentioned earlier, is the integral from a to b of f of x dx, divided by b minus a. This is the height of a rectangle with a base from a to b that has the same area as the region under the curve. The mean value theorem for integrals guarantees that if f is continuous, there exists some c in the interval where f of c equals this average value. For example, the average value of f of x equals x, squared on the interval from 0 to 3 is 1 over 3 times the integral from 0 to 3 of x squared dx, which equals 1/3 times x cubed over 3, evaluated from 0 to 3, which equals 1/3 times 9 equals 3. There's some point c where c squared equals 3. Specifically, c equals the square root of 3, where the function equals its average value. Probability is another field where integration is essential. For continuous random variables, the probability density function f of x satisfies two properties. F of x is greater than or equal to 0 for all x, and the integral from negative infinity to positive infinity of f of x dx equals 1. The probability that the random variable falls between a and b is the integral from a to b of f of x dx. For example, the exponential distribution has density f of x equals lambda times e to the negative lambda x for x greater than or equal to 0, where lambda is a positive parameter. The probability that x is between 1 and 3 is the integral from 1 to 3 of lambda e to the negative lambda x dx. The antiderivative is negative e to the negative lambda x. Evaluating, we get negative e to the negative 3 lambda minus negative e to the negative lambda, which equals e to the negative lambda, minus e to the negative 3 lambda. Differential equations involve equations containing derivatives. Solving a differential equation means finding a function that satisfies the equation. The simplest type is separable differential equations, where variables can be separated. Di over dx equals g of x times h of y. We rewrite this as 1 over h of y times di equals g of x dx, then integrate both sides. For example, di over dx equals xy. Separating variables, we get 1 over y di equals x dx. Integrating both sides, natural log of the absolute value of y equals x squared over 2 plus c. Exponentiating, the absolute value of y equals e to the x squared over 2 plus c, which we can write as y equals a times e to the x squared over 2, where a is a constant that can be positive or negative. Exponential growth and decay models come from the differential equation di over dx equals ky, where k is a constant. The solution is y equals y0 times e to the kt, where y0 is the initial value. This models population growth when k is positive and radioactive decay when K is negative. Suppose a bacterial population doubles every hour. If there are initially 1,000 bacteria, how many are there after 3 hours? The doubling time tells us that 2 equals e to the k times 1, so k equals the natural log of 2. After 3 hours, the population is 1,000 times e to the 3 times natural log of 2, which equals 1,000 times e to the natural log of 8, which equals 8,000 bacteria. For radioactive decay, if a substance has a half-life of 10 years, after t years the amount remaining is a 0 times e to the negative natural log of 2 over 10 times t. After 20 years, this equals a 0 times e to the negative natural log of 2 times 2, which equals a 0 times 1 over 4. 1/4 of the original amount remains, which makes sense. After 2 half-lives, you've halved twice. Logistic growth is a more realistic model for populations with limited resources. The differential equation is di over dt equals ky times 1 minus y over k, where k is the carrying capacity. The solution involves separation of variables and partial fractions, giving y equals k over 1 plus ae to the negative kt, where a is determined by initial conditions. This function starts with exponential growth, but levels off as it approaches the carrying capacity. Newton's law of cooling states that the rate of change of temperature is proportional to the difference between the object's temperature and the ambient temperature. If T is the object's temperature and T sub S is the surrounding temperature, then dt over dt equals K times T minus T sub S. This is another separable differential equation. Let's say a cup of coffee at 90 degrees Celsius is placed in a room at 20 degrees. After 5 minutes, it's 60 degrees. What's the temperature after 10 minutes? Using Newton's law, T of T equals T sub S plus T0 minus T sub S times e to the negative kt. Here, T0 equals 90 and T sub S equals 20. So T of T equals 20 plus 70 times e to the negative kt. At T equals 5, we have 60 equals 20 plus 70 times e to the negative 5k. So 40 equals 70 times e to the negative 5k, giving e to the negative 5k equals 4/7. At T equals 10, T equals 20 plus 70 times e to the negative 10k equals 20 plus 70 times e to the negative 5k squared equals 20 plus 70 times 16 over 49, which equals 20 plus 16/7 times 10, which equals approximately 43 degrees Celsius. Slope fields provide a geometric way to visualize differential equations. For di over dx equals f of x, y at each point in the plane, we draw a short line segment with slope f of x, y. These segments show the direction of solution curves. Without solving the equation algebraically, we can sketch approximate solutions by following the slope field. Euler's method is a numerical technique for approximating solutions to differential equations. Starting from an initial condition, we take small steps in the direction indicated by the derivative. If di over dx equals f of x, y, and we know y of x0 equals y0, then y of x0 plus h is approximately y0 plus h times f of x, 0, y0. We repeat this process, building a table of approximate values. The smaller the step size h, the more accurate the approximation. These topics give you a foundation in differential equations, though the subject extends far beyond Calculus 1. Understanding the basic concepts and being able to solve simple, separable equations prepares you for more advanced study. Throughout this section, we've seen that integration is remarkably versatile. From computing areas and volumes to solving differential equations and modeling physical phenomena, integration is an indispensable tool. The techniques we've learned, substitution, integration by parts, and various strategies for specific types of integrands, allow us to evaluate a wide range of integrals. However, it's important to remember that not all functions have elementary antiderivatives. Some integrals require numerical methods or special functions beyond the scope of introductory calculus. Modern computational tools can evaluate integrals numerically to high precision, but understanding the underlying theory and being able to work with integrals by hand remains essential. As we move to our final section, we'll tie together the major themes of Calculus 1, review key concepts, discuss common pitfalls, and look ahead to what comes next in your mathematical journey. We've now covered the core content of Calculus 1, from limits and continuity, through derivatives and their applications, to integration and its techniques. As we conclude this journey, let's step back and see the big picture. What have we really learned? How do these ideas connect? What are the common mistakes students make? And where do we go from here? Calculus is fundamentally about two things: instantaneous change and accumulation. The derivative captures instantaneous change, answering questions like how fast is this quantity changing right now? The integral captures accumulation, answering questions like how much has accumulated over this interval. What makes calculus beautiful and powerful is that these two operations are inverses of each other, connected through the fundamental theorem of calculus. Think about motion. Position, velocity, and acceleration form a chain of derivatives. Velocity is the derivative of position. Acceleration is the derivative of velocity. Going the other direction, if you know acceleration, you integrate to get velocity. If you know velocity, you integrate to get position. This connection between derivatives and integrals appears everywhere in science and mathematics. The concept of a limit underlies everything. Without limits, we couldn't define derivatives or integrals rigorously. The limit process lets us work with infinitesimally small quantities, turning intuitive ideas about instantaneous rates and infinite sums into precise mathematical statements. While you might not write out epsilon delta proofs in most applications, understanding that limits provide the rigorous foundation gives you confidence that calculus actually works. Let's review the major concepts we've covered. We started with limits, learning how to evaluate them using direct substitution, algebraic manipulation, limit laws, and special techniques like L'Hopital's rule. We discussed one-sided limits, limits at infinity, and infinite limits. We learned about continuity and what it means for a function to be continuous at a point or on an interval. From limits, we built the definition of the derivative as the limit of the difference quotient. We learned multiple interpretations of the derivative as the slope of the tangent line, as an instantaneous rate of change, as a linear approximation. We mastered the derivative rules: power rule, product rule, quotient rule, chain rule, and derivatives of all the standard functions including polynomials, exponentials, logarithms, and trigonometric functions. We explored applications of derivatives including related rates, where we find how fast one quantity changes given information about another. We studied optimization, finding maximum and minimum values of functions subject to constraints. We learned curve sketching, using the first derivative to find where functions increase and decrease, and the second derivative to determine concavity and inflection points. We discussed important theoretical results like the mean value theorem. Then we turned to integration, starting with antiderivatives and the indefinite integral. We learned that finding antiderivatives is the reverse of differentiation, though generally harder because there's no guaranteed algorithm. We studied the definite integral as a limit of Riemann sums, representing signed area under a curve. The fundamental theorem of calculus showed us how to evaluate definite integrals using antiderivatives, connecting the two branches of calculus. We learned integration techniques, including substitution, the reverse of the chain rule, and integration by parts, the reverse of the product rule. We explored more advanced methods for trigonometric integrals, trigonometric substitution, and partial fractions. We discussed improper integrals that involve infinite limits or infinite discontinuities. Finally, we examined applications of integration, including finding areas between curves, volumes of solids of revolution, using disk, washer, and shell methods, arc length, work, center of mass, and probability. We introduced differential equations, learning to solve basic, separable equations and understanding models for exponential growth, decay, and cooling. That's a tremendous amount of material. If you've understood even most of it, you've accomplished something significant. Calculus is challenging precisely because it introduces fundamentally new ideas that require new ways of thinking. You're no longer just manipulating symbols according to algebraic rules. You're reasoning about processes, limits, rates of change, and accumulation. Let's discuss common mistakes and misconceptions, because recognizing these pitfalls helps you avoid them. One of the most common errors is confusing when to use different derivative rules, especially forgetting the chain rule. When you have a composition of functions, you must use the chain rule. For example, the derivative of sine of x squared is not cosine of x squared. You need the chain rule, cosine of x squared times 2x. The key is recognizing the structure of the function. Is it a product, a quotient, a composition, or a combination? With a product rule, students often incorrectly think the derivative of f times g is f prime times g prime. That's wrong. It's f prime times g plus f times g prime. You differentiate each factor in turn while keeping the other factor unchanged, then add the results. For the quotient rule, remember it's low d high minus high d low over the square of what's below. The order matters. It's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. Sign errors are extremely common, especially with negative signs and subtraction. Always be careful when distributing negative signs through parentheses. When using the quotient rule, the minus sign in the numerator is easy to lose track of if you're not careful. With limits, a common mistake is thinking that if direct substitution gives 0 over 0, the limit doesn't exist. That's not necessarily true. 0 over 0 is an indeterminate form, meaning you need to do more work to find the limit. It might exist and be finite. It might be infinite, or it might not exist. You need to simplify, factor, use L'Hopital's rule, or employ another technique. For integration, forgetting the constant of integration c is a classic error with indefinite integrals. Every time you find an antiderivative, include plus c. For definite integrals, the constant cancels, so you don't include it. Incorrect application of substitution is another frequent problem. When you substitute u equals g of x, you must also substitute du equals g prime of x times dx. You cannot leave any x variables in the integrand after substitution. Everything must be in terms of u. If you can't eliminate all the x variables, the substitution probably won't work, and you need to try a different approach or manipulate the integrand first. With integration by parts, choosing u and dv poorly can make the problem harder instead of easier. The Lie heuristic helps. Choose u to be the first type that appears in logarithmic, inverse trig, algebraic, trigonometric, exponential. But this is a guideline, not an absolute rule. The goal is to make the integral of v du simpler than the original integral. In applied problems, setting up the problem correctly is often the hardest part. For related rates, you must identify all variables, write an equation relating them, differentiate with respect to time using the chain rule, then substitute known values. Don't substitute values before differentiating. You'll lose information. For optimization, you must express the quantity to optimize as a function of one variable, which might require using constraints to eliminate other variables. Units and physical interpretation matter in applied problems. If you're computing work, the answer should be in joules or foot-pounds or another appropriate unit. If the units don't work out, you've made an error. If you get a negative volume or a negative probability, something's wrong. Physical intuition catches many mistakes. Let me share some problem-solving strategies that help with calculus. First, always read the problem carefully and identify what you're asked to find. What information are you given? What do you need to determine? Draw a diagram if helpful. Visualizing the situation often clarifies the mathematics. Second, break complex problems into smaller steps. Don't try to solve everything at once. In a related rates problem, first identify variables, then write an equation, then differentiate, then substitute values. Each step builds on the previous one. Third, check your work whenever possible. After finding a derivative, differentiate your answer to see if you get back the original function. After evaluating a definite integral, check that your answer makes sense. Is it positive when the function is above the x-axis? Does the magnitude seem reasonable given the interval and function values? Fourth, practice, practice, practice. Calculus is not a spectator sport. You learn by doing problems, making mistakes, correcting them, and trying again. Work through many examples. Attempt problems before looking at solutions. Struggle is part of learning. Fifth, understand concepts. Don't just memorize formulas. If you understand why the chain rule works, you're less likely to forget to use it. If you understand the fundamental theorem conceptually, you'll remember how to apply it. Formulas are important, but understanding is deeper and more lasting. Let's briefly look ahead to Calculus 2 and beyond. In Calculus 2, you'll study more integration techniques, including trigonometric substitution, partial fractions, and strategies for choosing methods. You'll work with sequences and series, learning about convergence tests and power series representations of functions. Parametric equations and polar coordinates provide new ways to describe curves. You'll likely cover more applications like arc length and surface area in greater depth. Calculus 3, or multivariable calculus, extends calculus to functions of several variables. You'll learn about partial derivatives, multiple integrals, vector calculus, and concepts like gradient, divergence, and curl. This opens up applications in three-dimensional space, from electromagnetic fields to fluid dynamics. Differential equations becomes its own course, focusing on techniques for solving various types of differential equations and their applications. From modeling populations to analyzing electrical circuits to predicting weather, differential equations are essential in applied mathematics. Beyond these courses, calculus forms the foundation for advanced mathematics and virtually all quantitative sciences. Real analysis rigorously proves the theorems of calculus. Complex analysis extends calculus to complex numbers. Functional analysis studies infinite dimensional spaces using calculus concept. Numerical analysis develops computational methods for approximating solutions when exact answers aren't available. In physics, calculus describes motion, forces, energy, waves, electricity, magnetism, and quantum mechanics. In engineering, calculus is used for circuit analysis, signal processing, control systems, thermodynamics, and structural analysis. In economics, calculus optimizes utility functions, analyzes marginal costs and revenues, and models economic growth. In biology, calculus models population dynamics, disease spread, enzyme kinetics, and neural activity. In chemistry, calculus describes reaction rates, thermodynamic processes, and quantum chemistry. In computer science, calculus appears in machine learning, computer graphics, algorithm analysis, and optimization. The techniques you've learned are tools for understanding the world. Mathematics is the language of science, and calculus is perhaps the most important dialect. When a physicist wants to describe how a ball falls or a planet orbits, they write differential equations. When an engineer wants to minimize the cost of producing a certain output, they use calculus optimization. When a biologist wants to predict population changes, they model growth using derivatives and integrals. But calculus is more than just useful. It's intellectually beautiful. The fundamental theorem of calculus is an elegant connection between two seemingly different ideas. The epsilon-delta definition of a limit is a triumph of precise mathematical thinking. The techniques we've developed show human ingenuity in solving problems. Calculus represents centuries of brilliant minds wrestling with deep questions about infinity, continuity, and change. As you continue your mathematical journey, remember that calculus is both an end and a beginning. It's the culmination of your pre-calculus education, bringing together algebra, geometry, and trigonometry. But it's also the gateway to higher mathematics and advanced applications. Everything you learn from now on will either use calculus or build upon it. Some final advice. Be patient with yourself. Calculus is hard. Everyone struggles with it. The fact that you find it challenging doesn't mean you're not good at math. It means you're learning something genuinely difficult and worthwhile. Persist through the confusion. Work problems even when they're frustrating. Ask questions when you don't understand. Study with others. Use multiple resources. Textbooks, videos, online materials, tutors, professors. Don't just aim to pass the class. Aim to understand. Aim to see the beauty in the mathematics. Aim to appreciate why calculus matters and how it connects to the world around you. When you truly understand calculus, you see the world differently. You recognize rates of change everywhere. You think about accumulation and total change. You understand that complex phenomena can be analyzed by breaking them into infinitesimal pieces. Calculus trains your mind to think abstractly and rigorously. It develops problem-solving skills that transfer to other domains. The logical reasoning, the careful manipulation of symbols, the translation between verbal descriptions and mathematical formulations, all these skills are valuable far beyond mathematics itself. Whether you become a mathematician, scientist, engineer, economist, doctor, programmer, or pursue any other career, the thinking skills you've developed, studying calculus, will serve you well. You've learned to tackle complex problems systematically. You've learned to check your work and correct mistakes. You've learned that confusion and difficulty are part of learning, not signs of failure. As we conclude, let me emphasize the interconnectedness of calculus. Limits enable derivatives and integrals. Derivatives describe how functions change locally. Integrals accumulate those changes globally. The fundamental theorem ties everything together, showing that integration and differentiation are inverse operations. Techniques from one area often illuminate the other. Understanding the chain rule helps with substitution. Knowing the product rule helps with integration by parts. Calculus is a unified subject, not a collection of disconnected techniques. As you solve more problems and see more applications, you'll develop an intuition for how the pieces fit together. You'll start to see patterns. You'll recognize when a problem calls for derivatives versus integrals, which technique to apply, and how to set up the mathematics to model a real-world situation. The concepts we've discussed, limits, derivatives, integrals, the fundamental theorem, are among humanity's greatest intellectual achievements. They were developed over centuries by some of the finest minds in history. Newton, Leibniz, Euler, Cauchy, Riemann, and many others contributed to building this magnificent structure. You've now learned the foundations of their work. You have the tools to analyze change and accumulation, to optimize and approximate, to model and predict. You can find the slope of any curve, the area under any reasonable function, the maximum of a constrained quantity. You can solve differential equations that describe growth, decay, and equilibrium. You understand both the computational techniques and the conceptual foundations. This knowledge opens doors. In your future courses, you'll use calculus constantly. When you encounter a differential equation in physics, you'll know what it means and how to approach it. When you need to optimize a function in economics or engineering, you'll know how to find critical points and test them. When you read a scientific paper using integrals to compute probabilities or expectations, you'll understand what's happening. More importantly, you've joined a tradition of mathematical thinking that spans cultures and centuries. You're part of a community of people who see the world through the lens of mathematics, who appreciate the power of abstract reasoning, who understand that seemingly arcane symbols and formulas actually describe the deepest patterns in nature. Congratulations on completing this journey through Calculus. You've worked hard to master difficult material. You've persevered through confusion and frustration. You've developed new ways of thinking about functions, change, and accumulation. Whether you continue with more mathematics or apply what you've learned in other fields, the skills and insights you've gained will serve you throughout your life. Remember that calculus is not just about getting the right answer. It's about understanding why methods work, recognizing patterns, making connections, and appreciating the elegance of mathematical reasoning. It's about developing the persistence to work through hard problems and the humility to admit when you don't understand something. As you move forward, keep asking questions, keep working problems, keep seeking deeper understanding. Mathematics is a vast and beautiful landscape, and calculus is one of its most important regions. You've now mapped the major features of this territory. There's always more to explore, more connections to discover, more applications to learn. The calculus you've learned is centuries old, but it's also thoroughly modern. It's used every day by researchers pushing the boundaries of science and engineers building new technologies. The same derivatives and integrals Newton used to describe planetary motion now help land spacecraft on Mars, model climate change, develop medical treatments, and train artificial intelligence systems. So as we reach the end of this video, I hope you feel both accomplished and excited. Accomplished because you've learned a substantial and challenging subject. Excited because you've gained powerful tools that open up so many possibilities. You're now prepared for calculus, for physics and engineering courses, for quantitative work in any field. Keep learning, keep exploring, keep appreciating the beauty and power of mathematics. Calculus is not the end of your mathematical journey, but a crucial milestone along the way. Everything you've learned here will serve as a foundation for what comes next, whether that's more advanced mathematics or applications in your chosen field. Thank you for joining me on this journey through Calculus Y. I hope this video has helped you understand not just the techniques but the ideas, not just the how but the why, not just the mechanics but the meaning. Calculus is a profound and beautiful subject, and I hope you've come to appreciate its elegance and power. Good luck with your continued studies, and may your mathematical journey be rewarding and fulfilling.